every square matrix satisfy its own characteristic equation. So just to verify this theorem on this given particular matrix, first we need to get the characteristic equation of this matrix. So for that we'll write the characteristic matrix here. This is 1 minus lambda, 0, 0 and 2 minus lambda. And now we'll expand this characteristic matrix to get the characteristic equation. So this would be 1 minus lambda multiplied by 2 minus lambda. We'll open it. So this would be 2 minus lambda minus 2 lambda and plus lambda square. So the characteristic equation comes to be 2 minus 3 lambda plus lambda square. Now we need to verify Cayley-Hamilton theorem, which means we need to replace lambda here by a and this should come equal to 0. So just for that we'll replace lambda. So this is 2 minus 3a plus a square. Okay, so we have this matrix A here. We need to get this a square. So let us calculate the a square matrix here. So a square can be calculated by multiplying the matrix itself. This is 1, 0, this is 0, 2, this is 1, 0, 0, 2. So if you have a problem in matrix multiplication, I have already made a video on how to multiply matrices very fast. You can watch that video based on the matrix multiplication. Here to multiply this, we will multiply this row by column. So this would be equal to 1 into 1, that is 1, 0 into 0, that is 0. Then 1 into 0, that is 0, 0 plus 2, that is also 0, 0 into 1, that is 1, and 0 into 1, that is 0, plus 2 into 0, that is also 0, lastly 0 into 0, that is 0, plus 2 into 2, that is 4. So a square comes to be 1, 0, 0 and 4. Now we need to replace these two matrices A and A square here in the equation. This becomes 2 dot I. Here we can write I, identity matrix. So this is 2 dot I. Identity matrix for 2 by 2 matrix would be 1, 0, 0, 1. Next is plus, this is a minus sign. So we will use minus 3. Here we have to supply A. This is 1, 0, 0 and 2. Then we will write plus square. So what is A square? We had just calculated 1, 0, 0 and 4. Now we need to solve this. This is the matrix addition we need to perform. This can be done because all the square matrices are of the same order. So this would be 2 minus of 3 plus of 1. So 2 minus 3 plus 1, that is a 0 on first position. In second position, this is 0, this is 0 and this is also 0. So it will remain 0. In this position, this is 0, this is 0 and this will also be 0. So this is a 0. Last, this is 2, 2 into 1, that is 2. Minus 3 2s are 6. So 2 minus 6 plus 4, which is also a 0. So here it is a 0. You can see on the right hand side, this is coming 0. So you can say we have verified the Cayley-Hamilton theorem that this is true for the square matrix given here. So this square matrix satisfying its own characteristic equation. This is the Cayley-Hamilton theorem. In the next lecture, we will see how we can find out the inverse of the matrix using Cayley-Hamilton theorem.